Welcome to episode 1 of Mr. Warren's Audio Hood. This is the first part of my audio training series intended for general AV technicians, church sound crews, or anyone who wishes to better understand the audio craft. I would imagine that many of you have at least used the most basic of audio equipment, but for those who don't normally deal with the audio part of the staging or AV business, I have to start from the very beginning, with the absolute most basic of information. You have to walk before you can run, as they say. Even if you have worked in the business for a while, it will be worth your time to truly understand the how and the why. I'm not just going to teach theory and science. I'm going to teach you how to actually apply the knowledge you have learned in a practical way. We have to briefly examine the role of Ohm's law as it affects everything we deal with. The mixing console cannot function without it. No electronic device would function without it. The three symbols in Ohm's law, I, E, and R, represent three parameters as shown in this diagram. I is current in amps, E is voltage in volts, and R is resistance in ohms. Many of you are asking now, R is resistance, we get that, but I and E, why not V and C for voltage and current? Or just V and A for voltage and amps. In terms of a mathematical equation, you could substitute any letter you want, so long as the correct parameter is attached to it. But for explanation, I is for induced current, E is for electromotive force, and R, of course, is for resistance. Basically put, voltage is pressure, current is speed, and resistance regulates speed. It's seriously oversimplified, but that is the basic illustration. The simplest way to explain the theories is with the example of a water hose, spigot, and a nozzle. If we have a little trough of water and we place a foam block in it, and then connect a garden hose with a nozzle to one end and a spigot at the other, we can demonstrate these concepts in the physical world. If we set the nozzle to its widest opening, as you would when you mist the lawn, or something like that, want a light spray on something just to spray your bushes or whatever the case might be, and open the spigot up, the flow from the hose will move the foam block. If we attach a rock to the foam block, the block will not move unless we open the spigot, which creates more pressure, or narrow down the opening of the nozzle, which creates more speed. The work being accomplished is the movement of the foam block with the rock. The added weight the rock adds to the foam block becomes a resistive load, and as we open the spigot, this creates more force, or open the nozzle for more speed. The pressure and speed combine as more power, as is required to move that foam block and rock combination. And here it is again in slow motion. Power in the electrical world is measured in watts. If we look at the illustrations of Ohm's law again, we can see the relationship between resistance in the block, demanding more current, and or pressure to be moved. As an example of how Ohm's law works, we will use a simple LED. Unless you've been living in a cave in Borneo, you know what an LED is. They're everywhere. LEDs, light-emitting diodes, is what the word LED means, are referred to as current or constant current devices. That means regardless of the voltage present, the LED can only draw so much current. This is where resistance comes in, to regulate the current draw to the LED. Most common LEDs, like the ones you would find as an indicator light in any device that comes on when the device turns on, draws no more than 20 milliamps. It's limited to 20 milliamps. If you hit it with more current than that, it'll just simply blow up. It will, not in a physical sense, but it'll glow really bright and it's gone, and that's it. It burns out. So a typical LED itself will not turn on until it sees about 3 volts. So if we follow the law as such, 3 volts on the diagram divided by 0.020 amps or 20 milliamps works out to 150 ohms. So even at 3 volts, we still need a resistor with a value of 150 ohms to keep the current in the correct range. A resistor is used in this situation, as it is used in this situation, I should say, is referred to as a current limiting resistor, or a ballast resistor, or as a bias resistor, depending on who you're talking to. If we want a practical example, let's imagine we want to add a little indicator light to your car. Unless you're driving a pre-1964 Volkswagen Bug, your car runs on a 12-volt battery. So we know that the voltage is 12 volts. We start with that. So 12 volts divided by 0.020 equals 600. So in that case, you would need a 600 ohm resistor as a ballast for the LED in your car. So if we take that a bit further, how much power is the LED using? So according to Ohm's law, if we multiply 12 volts times 0.020 amps, we get 0.240 watts or 240 milliwatts. If we look at the basic 3 volt setup, we take 3 times 0.020 and we get 0.060 watts or 60 milliwatts. If, for example, we decided the LED needed to work at 120 volts, we take 120 times 0.020 and we get 2.4 watts. The only thing we'd have to be aware of at that point is if we're using a bigger resistor in terms of its power handling capacity, it winds up being a physically bigger resistor than the common resistor as pictured. In that case, you would have to put a resistor capable of handling at least 3 watts to be safe. If we look at this typical mixer, the spigot is a decent comparison between the input trim of the channel, while the nozzle we've seen in our previous example is a good representation of the output channel fader. The difference between that little field mixer and this huge 72 input Neve studio console are not as great as you might think. As I will explain, this little E&G field mixer may not appear to have anything in common with this huge studio console, but on a purely functional level, there's actually more in common than you might think. The objective of this course is not to teach you how to operate that huge mixing console. Again, you have to walk before you can run. This field mixer and this very basic stage mixer are a good starting point. Every audio mixer at its most basic level is an amplifier. This triangle symbol on this basic schematic is the standard electronic symbol for an amplifier. Amplifiers are basic. A weak signal comes in the input side of an amplifier, and a stronger signal comes out the output side. This increase in strength is referred to as gain. Within a mixer, there are occasions where an incoming signal is coming out at the same level or strength as when it came in. This particular situation is referred to as a unity gain situation, even though within the mixer, it may eventually or ultimately be mixed or combined with other signals. An example of when that might occur is if you connect some electronic device like a CD player or a computer or other thing that's powered and has an output to the mixer's input. We'll explore the reasons for that a little bit later in the episode. Many of you may be thinking, well, can't you just simply combine a bunch of outputs of things together with some cables and plug them into an amplifier and be done? The answer, that in a pinch you could do something like that, and it does happen from time to time. But for that to work, all the sources have to be of a same or similar level. In other words, you could take 2 CD players or 2 Blu-ray players and plug them into an amplifier with a couple of Y cables so you can share the inputs of the amplifier and simply use the amplifier's volume control as a volume control. It's crude, and effective, and it's something that occasionally has to be done because that's what there is. It's not desirable and it's not correct, but it would work in a pinch, as I said, only in a pinch. Problem comes when we have a basic microphone and we want to combine that with that same CD player. A microphone's output level is too weak to be able to balance against the CD player. Its signal would just simply get buried by the output of the CD player. A typical microphone's signal level or signal output level is said to be minus 56 dB volt, which is coincidentally called microphone level. Actual microphones vary wildly in real life. A cheap dynamic microphone, as pictured in the diagram, might put out only negative 56, while a professional condenser microphone might put out negative 40 to negative 30 dB volts. A typical professional CD player or similar thing will put out between negative 10 and plus 4 dB volts, which is a huge difference when compared to negative 56 or even negative 40 or negative 30. This is where the mixer becomes necessary. You can then feed the CD player to one input and the microphone to another input, and you can balance the levels out between the two by using the mixer. You will note that most mixers have the same basic structure: an input trim or a gain control, and an output channel control of some type, either a fader or a rotary pot, in a very, very basic mixer, as is the field mixer. Some of you are now saying, but wait, that channel is labeled input 1 or whatever. That fader is also the input channel, right? That fader is the output fader for that channel. That output of that channel is what determines what gets sent out to the world. In other words, it leaves that output channel fader, or shall we say the channel output fader more correctly, and goes to the master bus within the mixer, which has usually a master output fader for the entire mixer that actually goes to the world. If you turn down that individual channel output fader to nothing, nothing goes out. This picture is of a Midas Heritage 3000 console. It has 48 inputs, but don't let all the knobs frighten you. It is basically just 48 copies of the same thing from a functional standpoint. And each of those 48 channels has, as you guessed it, an input trim, usually at the top near the meter bridge, and an output channel fader down to the bottom close to where your hands would be. Now, the next thing we'll discuss is how to actually set proper gain structure within your mixer. When dealing with simple basic mixers like this, the best thing to do before you hook any speakers up to it or have any amplifiers on or connected to it is to work on the gain within the mixer. The safest way to do this is to do this before you've hooked any amplifiers or powered speakers or anything like that to the mixer. At this point, you simply want to work on the gain staging within the mixer so you have a clean starting point. To set this up correctly within the mixer, we need to take the mixer's main output fader and set it to its nominal position. If the mixer has a VU meter of some type, this is a helpful tool. Next, we open the channel output fader to its nominal position, as indicated by the picture. We then plug a microphone or CD player, whatever our source is, to the input of the mixer, and slowly open the trim pot until the VU meter hovers roughly between minus 10 and 0. The reason you want to start, you don't want to go to 0, which some people would say, well, it's logical. 0 is the nominal operating level for the mixer. That's correct, except for the fact that if you have 5 or 6 sources all set to 0, hitting that master bus, 6 of them will all sum together, which is the mixer's job to sum signals together, will overload that master bus. So to make the math work out within the mixer, even though we're dealing with an analog environment, it's safer to start about minus 10 on everything. That way you have what's referred to as headroom, and you're less likely to peak out or overload the master bus of the mixer. These concepts, when taken together, are what is referred to as gain staging, or gain structure. If we take that a step further and have an amplifier or powered speaker connected to the mixer's main output, with the gain staging set as described, and we happen to find that things are a little bit too loud for the room we're working in, The best solution to adjust the room volume is, if you have gain controls on your amplifier or powered speakers, is to turn those down until you get the desired result. If you have a much simpler scenario, say you're feeding this small staging mixer we described into a ceiling system, in other words, in a conference room that has speakers in the ceiling that have an amplifier located out of the room and out of your control, and all you have is a physical input connector in the room to it, you may at that point have to use the mixer's main output fader to control your room volume. In some basic AV setups, that's not an uncommon thing to do. It isn't necessarily desirable, but it's a workable solution. While the goal in using a typical mixer is for the input channel faders to be set around nominal, some adjust in the course of the show, either slightly above or slightly below is not unusual. What you should not wind up with is something that looks like this. Typically, if I walk into a setup and see this, I know immediately the mixer was not gain staged correctly. The biggest problem is if you find that you can only open the fader a little tiny bit, like 10 or 20% of its range, before things become really loud or overload the main output. That means that in the first place, your input trim settings are incorrect, and you are now operating the fader within a very short throw. If you look at the way the fader is marked in that bottom 20%, the jump in gain is from -60 to about -30 in most cases. That's a huge jump in gain in such a short distance. On the other hand, if you get to the top or more nominal operating range of the fader, the gain changes between the little marked positions on the fader track are more subtle. 4 dB, 5 dB, 6 dB. So you can move a little tiny bit and only move a dB or two. So it's more subtle and makes for a much more smooth show. You'll notice the weird scaling on a audio fader track is these strange jumps like that is because the audio fader track is a logarithmic device. Whereas on a lighting console, it's in 10% increments in what's referred to as a linear fader track. Some of you may ask the question, what about a digital mixer? Even the most expensive digital mixers are still based on the idea of emulating the functions of an analog mixing console, at least on a basic level. I'm not going to get into the specifics of digital mixing consoles at this stage in the game, but I will address them in a later episode. I will highlight some very basic thoughts here. Generally, the distinction between an analog and digital console is this. Analog devices and analog mixing consoles manipulate voltage and current based on analog equivalents or representations of the original source signals. In simple terms, if you put a signal that is 10 millivolts into the mixer and is set up to amplify that mixer by a factor of 100, then you get 1 volt on the output. It's very oversimplified, but that's basically the concept of how an analog device functions. Whereas with a digital mixing console, those same analog signals are converted into numerical data, which can be stored, manipulated, and altered mathematically. A digital mixing console, of course, mimics an analog console on a basic level by converting those signals into numerical representations, which can be manipulated mathematically, as I stated. A simple example is that the summing of the two signals in a mixer is basically a mathematical algorithm that the internal computer says A plus B equals the sum of A plus B. Other functions like equalizers and reverbs and compressors and things like that are accomplished with far more complex algorithms than that. The takeaway is the same gain staging rules apply to a digital console as they do to an analog console. It's what happens to the signals inside the digital mixing console that make up the prime difference in how it operates. If you are new to audio, you should generally avoid using more sophisticated digital mixing consoles until you are much more comfortable. In a basic sense, as I said, they operate like an analog console. But where you get into trouble is in some of the more sophisticated consoles, there can be not only several menu screens deep of things in a touchscreen menu or otherwise, each fader on a digital console can serve several different functions according to how it's been built or assigned or programmed by the operator. So you can very easily get lost in your position on where you are in operating the console if you're not familiar with it or haven't had a lot of time on consoles of that sophistication, which could make for a very stressful and unpleasant experience for you for your first time out trying to do that. The unit we have pictured on screen here is a QSC Touch Mix. The QSC Touch Mix is an affordable, basic digital console. This particular version on the screen is the 24 input version. It's also available in 8, 16, and 30 input versions. In terms of features and their user interface, the whole thing is touchscreen driven. The only analog control on the unit is a small trim control for each input channel located directly beneath the connectors. As with most recent digital mixing consoles, the Touch Mix units can also be operated by a tablet computer or even a smartphone like this one. The purpose of this series of instructional podcasts is not so much to teach the specifics of operating any one piece of equipment. There are plenty of how-to videos created by both users and the manufacturers, which are often a great resource, particularly with certain digital consoles, available at YouTube. Even the most experienced engineers will occasionally be handed a new device they haven't seen recently or at all, and they have to learn some function that they're not familiar with, which may not be obvious in looking through the manual or looking through the menus on the console. Quite often, it's quick and easy enough to pick up your phone or your tablet or computer and go to YouTube and look up the particular instructions for that device. And somebody may have had the same situation where they might go, I need to know how to accomplish this task. Well, here's how I did it. And they'll post a thing on YouTube of this is how I did X and Y. Even if you've been in the business for a little while, hopefully you will learn something new from this and will take a more methodical approach to your setups. Even if you are very new to the business, hopefully by learning the fundamentals correctly, you won't pick up the bad habits that come from being thrust into situations in a panic and get in the habit of just simply making things work. Instead, learn how to make it work correctly. That's all for this episode, but feel free to drop by the Audio Hood anytime. We'll have the next episode up fairly soon. Thanks for tuning in.